For most of mathematics, we've used a system called Cartesian coordinates to identify where a point sits in a graph. Here we're going to learn about a new system called polar coordinates. In a Cartesian graphing system, when we identify a point, we use its vertical and horizontal distances to identify its location. We call the horizontal distance x, and we call the vertical distance y. And then we label the point as x, y. However, we can think of some other ways that we might measure or locate that point. The polar system uses its distance from a central point called a pole and an angle to locate the point. If we situate the pole at the origin in our Cartesian system and draw a line segment to our point, the length of that segment, we'll call that r. Notice that that segment makes an angle with the positive x-axis. We're going to call the positive x-axis the polar axis. And we'll call the angle between our segment r and the polar axis theta. Then any point in the plane can be uniquely identified by its distance from the pole and its angle with the polar axis, and we can write its coordinates as r, theta. Notice that if we use basic trigonometry, we get some relationships between these values. We can see here, by using the Pythagorean theorem, that r squared is equal to x squared plus y squared. We can also see that the sine of theta is equal to y over r, or in other words, y is equal to r sine theta. Similarly, the cosine of theta is equal to x over r, so that x is equal to r times the cosine of theta. Lastly, we can see that the tangent of theta is equal to y over x. These four relationships give us a way to move back and forth between our Cartesian coordinate system, where the point is identified as x, y, using its vertical and horizontal distances from the origin, and the polar coordinate system, where a point is identified as r theta, using its distance from the pole and its angle with the polar axis. There are a few important things to note about points when we identify them using their polar coordinates. If we take a point r theta, knowing that the segment connecting it to the pole is of length r and the angle it makes with the polar axis is theta degrees, we can identify a point in the opposite direction where this distance is also r. The coordinates of this point are going to be negative r theta. So in other words, the point r theta and the point negative r theta are images of one another through the origin. Given this relationship, it's also the case that the point r theta and the point negative r theta plus pi are the same point. It's also the case that r theta and r theta plus 2 pi or minus 2 pi are the same point. So for any point we write within the polar coordinate system, we have multiple ways of identifying that point by changing the sign of r or adding multiples of pi or 2 pi to the angle theta. So summing all that up, we can identify a point in a plane as either xy, using its vertical and horizontal distances, or as the point r theta, where r and theta represent a length of a segment and an angle. And the relationship between those two are given by the following. X is equal to r cosine theta, y is equal to r sine theta, x squared plus y squared equals r squared, and the tangent of theta is equal to y over x. We also know that the point r theta and the point negative r theta are reflections of one another through the origin, and r theta, negative r theta plus or minus pi, and r theta plus or minus 2 pi are all equivalent ways of identifying the same point. We'll use these relationships now to look at a few examples. Let's see if we can use the rules we just talked about in order to rewrite the point p 2 comma pi over 3, which is given in polar coordinates, in two other ways. So we know, first of all, that the point r theta and the point negative r theta plus or minus pi are equivalent. So in other words, we can rewrite p as negative 2 pi over 3 plus pi, which is of course the point negative 2 4 pi over 3. Similarly, we know the point r theta and the point r theta minus 2 pi are the same. So we could write this as p 2 pi over 3 minus 2 pi, which is the same thing as 2 negative 5 pi over 3. Now that we have a few different polar versions of that point, let's see if we can write it using Cartesian coordinates. So we're starting off with the polar point 2 comma pi over 3. We know that x is going to be equal to r times the cosine of theta. So in this case, x is 2 times the cosine of pi over 3. Similarly, y is going to be r times the sine of theta, which will be 2 times the sine of pi over 3. Since the cosine of pi over 3 is 1/2, we get 2 times 1/2 here, which is 1. And since the sine of pi over 3 is root 3 over 2, we get the square root of 3. And so in polar coordinates, our point was 2 pi over 3. In Cartesian coordinates, our point is 1, the square root of 3. We can use our relationships to change more than just points. We can also change polar equations into Cartesian equations. So here we have the equation r equals the cotangent of theta times the cosecant of theta. And we want to rewrite that using x's and y's. Rewrite this so that it might be a familiar graph in our Cartesian system. So the first thing we ought to do is switch everything into sines and cosines, because the relationships that we have involve sines and cosines rather than cotangents and cosecants. So cotangent of theta is the same thing as cosine of theta divided by sine of theta, and cosecant is 1 over the sine of theta. So we get here that r is equal to the cosine of theta over the sine squared of theta. If we multiply both sides by sine squared, we get the relationship r sine squared of theta is equal to cosine of theta. Now, our left side looks suspiciously like our relationship y equals r sine theta, except we have an extra sign in it. So here we have to use a little bit of a trick. What we're going to do is we're going to multiply our entire equation by r. That then gives us that r squared sine squared of theta is equal to r times the cosine of theta. Now, not only do we have our relationship y equals r sine theta in there, but we also have our relationship x equals r cosine theta in there, so that this equation becomes, first we'll rewrite the left as r sine theta squared, so that we can very obviously see now that this is the Cartesian equation y squared equals x, which we know is a parabola. It has its vertex at 0, 0, and it opens to the right. Of course, if we can go from polar to Cartesian, we should be able to go the opposite direction as well. So here we're going to convert x minus 1 squared plus y squared equals 1 into polar coordinates. Notice that that is a circle that has a radius of 1 and its center is at the point 1, 0. We're going to use our familiar relationships, x equals r cosine theta and y equals r sine theta, to replace x's and y's in this. So this is going to become r cosine theta minus 1 squared plus r sine theta squared equals 1. We'll expand this out so we get r squared cosine squared theta minus 2r cosine of theta plus 1 plus r squared sine squared of theta is equal to 1. We can combine some terms here. We'll put the r squared cosine squared theta and the r squared sine squared theta together. And we can move the 1 to the other side and we get a 0 then. Here we can factor out an r squared and we're left with cosine squared theta plus sine squared theta, which we know is equal to 1. That gives us r squared minus 2r times the cosine of theta is equal to 0, which we can write as r squared equals 2r cosine theta. And then we can divide both sides by r to get that r is equal to 2 times the cosine of theta, which is in fact going to be a circle with radius 1 and center at 1, 0. Summarizing what we know, if we have a point, xy, in the Cartesian coordinate system, x represents its horizontal distance from the origin and y represents its vertical distance from the origin. We can rewrite that as a point in the form r theta, where r represents the length of the line segment connecting the point to the pole, typically placed at the origin, and theta represents the angle created by that segment of length r and the polar axis. We can move between these two systems by using the relationships x equals r cosine theta and y equals r sine theta. X squared plus y squared equals r squared, and the tangent of theta is equal to y over x. We also have several different ways of representing the same point within the polar system by adding or subtracting variants of pi and 2 pi to the original point.